Good day everyone, my name is Jonas and I will discuss to you about Antipodal Vivaldi antenna. At Vivaldi antenna. A Vivaldi antenna or Vivaldi aerial or covered slat antenna is a coplanar broadband antenna which can be made from a solid piece of sheet metal. A printed circuit board or from a dielectric plate metallized on one or both sides. The feeding line excites an open space via a microstrip line or a coaxial cable and may be terminated with a sector-shaped area or a direct coaxial connection. From the open space area, the energy reaches an exponentially tapered pattern via a symmetrical slat line. Vivaldi antennas can be made for linear polarized waves or using two devices arranged in orthogonal direction for transmitting or receiving both polarization orientations. If feed with 90-degree phase shifted signals, orthogonal devices can transmit receive circular-oriented electromagnetic waves. Vivaldi antennas are useful for any frequency as all antennas are scalable in size for use at any frequency. Printed circuit technology makes this type antenna cost-effective at microwave frequency exceeding 1 GHz. This inexpensive Vivaldi antenna is etched upon a printed circuit board and fed with a soldered-on coaxial cable and SMA connector. Advantages of Vivaldi antennas are their broadband characteristics, suitable for ultra-wideband signals, their easy manufacturing process using methods for PCB production, and their easy impedance matching to the feeding line using microstrip line modeling methods. The Vivaldi antennas was first described and characterized in 1979 by Gibson. Later, the Antipodal slat line suggested by Yazid also referred to as symmetric double-sided slat line was constructed with microstrip feed as an input feed to increase the performance of the antenna. The slat line was used as radiation mechanism and hypered script improves the transition region. Jonas et al. Used this idea to construct a Vivaldi antenna and have shown good results over a wide frequency range by maintaining a transition region from 3 to 5 wavelengths long distance to avoid a discontinuity between a feed and the receiving regions. The Antipodal Vivaldi antenna is a wideband and symmetrically enriched plane that has been used extensively in radar applications, wireless communication applications, and dual polarization applications. More recently, the Vivaldi antenna has been identified as being suitable for ultra-wideband application, with increasing interest in UWB as viable radio architecture. The Vivaldi antenna has attracted interest due to its theoretically infinite bandwidth. It is a directional antenna with end-fire characteristics. The polarization of a single radiator is linear. The electric field lines are parallel to the printed circuit board material. The printed boards with the antenna groups can also be nested crosswise or a second plane of polarization. The beam direction of the antenna is the direction in which the conical slat expands. So here's some questions about the topic. Number 1. Vivaldi antenna made of what kind of materials? A. Printed circuit board. B. Solid piece of sheet metal. C. Dielectric plate. Or D. All of the above. The answer is all of the above. Number 2, which is not true about antipodal Vivaldi antenna. A. A wide band and symmetric EMH plane. B. Used in radar application, wireless communication application, and dual polarization applications. C. Suitable for ultra-wideband applications, or D. None of the above. The answer is none of the above. Number 3 questions. FR4 is always utilized in the band of less than A. 1 GHz, B 2 GHz, C 3 GHz, or D 4 GHz. The answer is A. 1 GHz. Number 4 question. One of the layers is printed on top and the other one, which is tapered in opposite direction, is printed on the bottom of the dielectric substrate material. What type of Vivaldi antenna? A. Coplanar Vivaldi antenna. B. Antipodal Vivaldi antenna. C. Balanced antipodal antenna. Or D. None of the above. The answer is B. Antipodal Vivaldi antenna. Number 5. The Vivaldi antenna was first described and characterized in 1979 by A. Guglielmo Marconi, B. Ehud Yazid, C. E.J. Gibson, and D. Antonio Vivaldi. The answer is C. E.J. Gibson. 3 types of Vivaldi antennas. Number 1 is coplanar Vivaldi antenna. 2 is antipodal Vivaldi antenna, and 3 is balanced antipodal antenna. The coplanar Vivaldi antenna, 2 radiator planes are on the same side of the dielectric material. The antenna can be fed by a Arthur coupling from the other side as depicted. While the antipodal Vivaldi antenna is proposed to solve the fitting in coplanar ones. In this type of Vivaldi antenna, one of the layers is printed on top and the other one, which is tapered in opposite direction, is printed on the bottom of the dielectric substrate material. This antenna can be fed easily by soldering the connector to the sides of the PCB material. Last is yung balanced antipodal antenna. Consists of 3 upper layers. An dielectric layer has been added on top of the antipodal structure, and an additional metal plate, just like the one in the bottom of the antenna, has been printed on top of the newly added layer. The advantages. Vivaldi antennas are planar antennas that work over a wide frequency range. Like ridge or antennas, they have high gain due to their tapered slot design. Vivaldi fit into smaller spaces than a ridge horn antenna because they can be made out of flat laminate. Impedance matching is easy with Vivaldi antennas. Vivaldi antennas are usually ultra-wideband antennas and always thought as broadband antennas. They can be used with both multiband and impulse technologies. Next is when used for pulse technologies like radar, these antennas have a high peak value for the pulse envelope. They offer stable group delay and allow for a narrow pulse width. Their upper frequency is limited by the width of the gap, while the lower frequency is limited by the size of the opening. The design is simple compared to long periodic antennas and fractal device designs, and all antenna designs can be scaled for use at any frequency. The coplanar Vivaldi is the original design. It features 2 radiator planes on the same side of the dielectric strip, the other side of which is a neutral material design, and the more complex one can be made by a printed circuit board technology. Next, the disadvantages. If you only plan to use the Vivaldi antenna on one frequency or a small range of frequency, There are smaller and higher gain antenna designs. Gain refers to the ability of the antenna to radiate power in specified direction. Vivaldi can be fed by an aparatus copper or broadband balloon, but this can add complexity in design, making an antipodal Vivaldi antenna with the antenna elements printed on opposite sides of the PCB substrate is more expensive than the basic design. The antipodal Vivaldi antenna's impedance matching can be done through a transition from strip to a microstrip line. However, this design increases cross-polarized radiation. The The balance and economical balance and also prevents cross-polarized radiation by adding yet another dielectric sheet on top of the antipodal structure while a metal balance is put on both of the antenna. The downside of this design is that the cost of a printed circuit board is significantly related to the number of layers and complexity of the system. The balance of antipodal without the antenna or BAWA usually suffer from tilted beams and low axial aims. They cannot really be extended beyond 10 dBi of gain unless used as fish feed. Next is the basic structure and principle of antipodal Vivaldi antenna. The antipodal Vivaldi antenna consists of substrates and bonding copper on both sides of the substrate. It can be divided into two parts, radiation area and volume. Given that transmitting and receiving antennas are equivalent, the transmitting antenna was utilized to explain the basic principle. After an electromagnetic wave is transmitted from the balloon to the radiation area, it can radiate from the top and start to the free space. A low-frequency electromagnetic wave radiates from the wide area of the slot because of long wavelengths. Simultaneously, a high-frequency electromagnetic wave radiates from the narrow area of the slot. This is the main reason why the Vivaldi antenna possesses the characteristics of broadband and stable directivity. With this, if the wavelength of the electromagnetic wave is more than twice the maximum slot width of the Vivaldi antenna, it would not radiate efficiently and radiation pattern would gradually become similar to that of monopole. In the initial phase of antenna design, the substrate material should not affect the subsequent parameter calculation in antenna design. FR4 dielectric constant equals to 4.4 dielectric loss tangent 0.0 is often utilized as a substrate because of its low price. However, FR4 has two disadvantages. One is that its high dielectric loss tangent causes a large energy loss. The other is that FR4 from different manufacturers and various markets has different looping concentration which make the dielectric constant unstable. Controlling the characteristic impedance of the antenna is difficult, so FR4 is always utilized in the band of less than 1 GHz. In this study, Teflon was used as substrate. For figure number 4, simulate and return loss and realize in terms of antipodal antennas versus frequency. So letter B, 3D E-plane and HD radiation patterns of the antipodal antenna at 60 GHz. 3D E-plane and H-plane radiation patterns of the corrugated ABA at 60 GHz. The return loss curves of antipodal antenna and corrugated antipodal antenna are calculated using CST microwave studio and presented in figure 4A. It can be seen that adding corrugations has minor effect on Vivaldi antenna impedance matching and the matching bandwidth. Both antennas achieve wide and impedance matching bandwidth better than negative 10 decibels starting from 45 GHz up to 75 GHz. The maximum realized gain is also calculated for both antennas as shown in figure A. that if maximum gain is 13.5 decibel and 13.8 is dBi for antipodal antenna and corrugated antipodal antenna at 16 GHz respectively. The simulated radiation pattern polarization radiation patterns of EPA in both E and H planes at 16 GHz are present in Figure 4b. Figure 4c shows the simulated radiation pattern and copolarization radiation patterns of corrugated antipodal antenna in both E and H planes at 16 GHz. So here's the sample of images of some of antipodal antenna. So that is the end of my topic. Thank you.